Okay, thank you for introduction. Thank you for coming to my presentation. Today I'll be discussing XTM and presenting a practical case study highlighting its needs. First, a little bit about me. I'm Yuya Watari from Tokyo, Japan, and I'm working at NTT Open Source Software Center, Software Innovation Center, and developing distributed databases. My interests include distributed transactions, planning, optimization, and photography. Here is the agenda for today's talk. We will start with the introduction and then move on to the next part, making PostgreSQL distributed, where I will explain FDW-based sharding and raise the issues that this talk addresses. In the next part, making a transaction manager pluggable, I will present an overview of XTM, which allows the core transactional APIs of PostgreSQL to be replaced. Next, we will move on to the case study that highlights the potential of XTM to meet diverse user-specific needs. I will finish up with a discussion and then conclude this talk. Let's get started with the introduction. The keywords of this talk are transactional extensibility and XTM. PostgreSQL is well known for its high extensibility. However, while it has many hooks in the planner and executor and access methods, PostgreSQL lacks transactional extensibility. This is because it does not have any hooks or pluggable APIs for replacing the transaction manager. As a result, custom transaction methods cannot be implemented as extensions, and forking of the PostgreSQL core is required. A promising solution to this problem is the Extensible Transaction Manager, or XTM. XTM enables the core transactional APIs like snapshot mechanism or tuple visibility determinations to be replaced. XTM was first proposed in 2015 by Postgres Pro, but has not yet been implemented. The discussion in 2015 mainly focused on implementing state-of-the-art methods like global transaction managers or clock-based algorithms. Beyond such purposes, XTM plays an important role in complementing these existing methods to meet user-specific requirements. The requirements for distributed transactions vary from user to user, and there are various patterns of consistency. For example, some users want performance-oriented methods and others need consistency-oriented methods. Existing methods do not always satisfy these requirements, and until now, there has not been any discussion as to how using XTM can complement the existing methods. My objective with this talk today is to introduce a case study of utilizing XTM to complement existing state-of-the-art methods to meet user-specific requirements. The case study we conducted models a banking system where account information is distributed and located in multiple nodes. This figure shows data distributed in two nodes. Two types of queries are addressed, transfer and balance inquiry. In this case, there are two user-specific requirements. First, the system should support local transactions on shards to provide high performance. Second, it should ensure session consistency even for local transactions. We utilize XTM to complement the existing methods which fail to meet these requirements. Now, let's move on to making PostgreSQL distributed FDW-based sharding. As you know, FDW-based sharding is a common method to distribute tables among multiple shards in PostgreSQL. It is a combination of foreign data wrapper and table partitioning. FDW accesses remote data by SQLs and enables the use of external data sources as if they were local tables. A table partitioning splits the table into multiple partitions. In this case study, the table has account information and is distributed and located in multiple partitions and shards. As I mentioned in the introduction, in addition to standard global transaction support, such as atomic commit and atomic visibility, the user in this case study has two user-specific requirements. The first is to allow local transactions on shards. Transactions enclosed within a single shard should bypass the coordinator and be performed locally on the shard. This is to maintain high performance. And the second requirement is to ensure session consistency. If the user observes that a transaction has finished, a subsequent transaction should reflect the result. This must be applied to local transactions in this case study. Now I will provide a brief overview of methods for standard global transaction supports. Various state-of-the-art methods have been proposed to ensure atomic visibility. Global transaction managers or GTMs are common and they assign global transaction IDs to uniquely identify global transactions. This kind of method is called centralized coordination. Postgres XCXL is a well-known implementation of GTMs. Another option is clock-based algorithms like ClockSI, which uses loosely synchronized clocks to coordinate global transactions. A third option, pessimistic coordination, assigns local snapshots atomically when a global transaction begins. ClockSI and pessimistic coordination are forms of decentralized coordination. Now, let's move on to the system design used in this case study. We ensure atomic commit by 2PC with PostgreSQL+, which is a fork of PostgreSQL. This will be explained in the next slide. Atomic visibility is also ensured by existing state-of-the-art methods as I have mentioned. To support local transactions on shards, we assume the adoption of decentralized coordination. However, this design does not ensure session consistency, which the user in this case study requires. Let's take a closer look at PostgreSQL+, which supports 2PC. PostgreSQL is widely utilized to achieve FDW-based sharding. It is provided as a contribute module and enables the use of PostgreSQL servers as external data sources. However, it does not support distributed transactions. Therefore, in this case study, we use another FDW called the PostgreSQL+, which is a fork of PostgreSQL developed by NTT Data that supports atomic commit. Its basic usage is the same as that of the original PostgreSQL. Atomic commit ensures that a transaction is either fully committed or totally aborted in all participating nodes. This feature is essential in distributed transactions. PostgreSQL+ achieves atomic commit by a two-phase commit or 2PC protocol. This case study adapts PostgreSQL+ to support distributed transactions. Now I will explain atomic commit in detail. Naive transaction methods can lead to an inconsistent state. The slide shows naive one-phase commit. In this example, a transaction involves two shards, shard 1 and shard 2. If a user issues a commit command to the coordinator also issues a commit command to each shard. As you can easily imagine, this method is problematic. In this example, if a commit command to shard 1 is successfully executed, but the commit command to shard 2 fails, the global transaction falls into an inconsistent state. The TPC protocol is a solution to ensure atomic commit. It involves a prepare phase and a commit phase. In the prepare phase, the coordinator confirms whether a transaction is committable. If committable, the coordinator issues commit prepared to shards to finalize the transaction. If not committable, the coordinator instead issues rollback prepared to abort the transaction. In this way, the TPC protocol prevents transactions from having inconsistent states. Now I will describe how PostgreSQL Plus implements TPC. Here you can see the commit transaction function in the PostgreSQL core. This function is called when committing a transaction. The main operations of committing a transaction are in the middle of this function, which also has callbacks before and after the main operations. The pre-commit callback is allowed a returning error leading to abort transaction. The post-commit callback is not allowed a returning error. PostgreSQL Plus utilizes these callbacks to implement TPC. First, PostgreSQL Plus issues a prepare transaction command in the pre-commit callback. This is the first phase of TPC. If the prepare phase is successful, PostgreSQL Plus issues commit prepared in the post-commit callback. On the other hand, if the prepare phase fails in some nodes, the control flow moves to abort transaction. In abort transaction, PostgreSQL Plus issues rollback prepared to abort the global transaction. In this way, atomic commit is achieved. So far, I have explained the implementation of PostgreSQL Plus. Next, we will discuss the optimization of TPC protocol. The current PostgreSQL Plus returns acknowledgement after the commit phase of TPC. Here, returning acknowledgement at the end of the prepare phase is a typical optimization of TPC. Many other distributed databases adopt this optimization as well, which can improve various aspects of the performance, such as latency. To achieve high performance, we adopt this optimization in this case study. Unfortunately, under this optimization, the session consistency is not guaranteed. Let's take a look at an example of this scenario shown in the slide. There are two accounts A and B, located in shards A and B respectively. Initially, both accounts A and B have $10. When the user transfers $1 from A to B, account A will have $9 and B will have $11. If the user inquires the balance of B by a local transaction on shard B after this transfer, the user must observe the updated result of $11. In other words, the transfer must not be lost. We call this session consistency. The user in this case study requires this session consistency, but it is not guaranteed, so customization of the transaction manager is needed. Why is session consistency is not guaranteed? This slide shows the sequence of operations performed when the user issues transfer and balance inquiry transactions. we call transfer transaction global transaction 1. Shard A is here on the top and shard B is below. The slide shows that global transaction 1 load accounts A and B. Here, account B has $11. If the user requests a commit of the global transaction, PostgreSQL Plus issues a prepare transaction for each shard as I described earlier. At this time, assuming 2PC optimization has been done, acknowledgement is returned to the user at the end of prepare. Then the user knows that the transfer has been completed. Next, the user tries to confirm the transfer has been exactly and successfully done by starting local transaction 2 on shard B. In this transaction, the user issues the query for the balance of B directly to shard B bypassing the coordinator. At the beginning of this local transaction, a snapshot is taken and shard B reads the balance of B according to this snapshot before returning the result to the user. Here, the problem due to lack of session consistency arises. The read of account B is done according to the snapshot in shard B, but this snapshot was taken before commit prepared. In this snapshot, a global transaction 1 is in progress and invisible, so shard B returns an old result. This appears to the user as if the transfer has been lost and session consistency is broken. This is a problem that this case study addresses. The solution is to achieve session consistency by XTM. Specifically, we implement a custom transaction method ensuring session consistency even for local transactions by XTM. This is a user-specific method for a user-specific requirement. We customize snapshots and tuple visibility determination. XTM is effective for complementing existing methods to meet this kind of user-specific requirement, which is not always needed in general. Now let's review XTM, which makes the transaction manager pluggable. As I mentioned earlier, extensible transaction manager, namely XTM, significantly improves transactional extensibility in PostgreSQL. It allows the core transactional APIs to be replaced. Although XTM was first proposed nearly 10 years ago, it has not yet been merged into the PostgreSQL core. This is the proposed interface of XTM. It makes similar functions in the transaction manager pluggable. Each pointer in this structure encapsulates an original function in the transaction manager. Here, there is one important question. What do these functions originally do? We need to know the behavior of the transaction manager. From here, we will deep dive into the transaction manager. In PostgreSQL, MVCC is a basic and fundamental technology. Its architecture and implementation are important to understand the case study and XTM. MVCC stands for Multi-Version Concurrency Control. It achieves isolation with high concurrency. PostgreSQL's transaction manager assigns a transaction ID to each transaction and then obtains a snapshot when the transaction starts. Please note that this is the behavior when the isolation level is repeatable read or higher. For read committed, PostgreSQL obtains a snapshot for each command. The snapshot stores information about which transactions are committed, aborted, or in progress when the snapshot was taken. Next, an executor returns tuples that are visible according to the current snapshot. This is called tuple visibility determination. This slide shows snapshots in PostgreSQL. Again, snapshots hold information of which transactions are visible. In this example, blue boxes denote visible transactions and gray boxes denote invisible transactions. The snapshot has a field named xmin. All transactions whose transaction ID is less than xmin are visible in this snapshot. Similarly, all transactions whose transaction ID is greater than or equal to xmax are invisible. On the other hand, transactions between xmin and xmax have different visibility and may be visible or invisible. PostgreSQL snapshot stores their visibility in an array of snapshot data structure. Let's move on to the table structure. This slide shows visual examples of the tables in PostgreSQL. Each row has an xmin column and an xmax column. Xmin is the transaction ID that loads the tuple, and xmax is the one that deleted it. This information is used in the tuple visibility determination. This slide shows the state just after inserting one row, whose ID is 1 and balance is 10. The transaction ID that loads this tuple is 100, which is recorded as xmin. Here, no one deleted the tuple, so xmax is empty. Now we consider the process after updating the balance to 11. PostgreSQL appends an updated tuple to the table instead of modifying the tuple already in place. In this case, transaction ID 103 updated the balance. So the first tuple's xmax became 103 and a new tuple is appended. Next, we will consider scanning the table. Here, we scan the table according to the snapshot shown in the slide. During table scanning, the PostgreSQL executor checks the visibility of the tuples. The first tuple's xmin is 100 and this is visible in the snapshot. On the other hand, xmax is 103 and it is invisible. Since transaction ID 100 was committed, this tuple is visible and shown in the result. The second tuple's xmin is 103 and this is invisible in the snapshot. So this tuple is invisible and not shown in the result. Finally, the user sees the record whose balance is 10. Isolation in PostgreSQL is achieved in this way. Now, let's move on to the implementation. This slide shows the snapshot data structure, which comprises xmin, xmax, and xip. xip holds in-progress transaction IDs when the snapshot was taken. Snapshot data is a key in the PostgreSQL transaction manager. I will now describe how the table scanning is implemented. There are various types of scan depending on the tables and the queries. Here, we consider a point query as shown on the slide. A point query obtains data by specifying a specific column that has an index. As I explained previously, when a transaction starts, PostgreSQL obtains a snapshot. This is done by the getSnapshotData function. Then PostgreSQL starts executing the query. During execution, various functions are called, but the important ones here are the two functions at the bottom of this slide. Heap tuple satisfies visibility does exactly what its name suggests. It determines the visibility of a tuple. XID in MVCC snapshot is called at this time. This function checks whether a transaction exists in the snapshot. These functions are important in the tuple visibility determination. XTM provides an encapsulation of these functions. For example, it provides an encapsulation of the get snapshot data and XID in MVCC snapshot functions to replace the snapshot architecture. These encapsulations play a key role in the case study. Now, let's move on to the main topic of today's talk, the case study. First of all, we look back at the problem in this case study. The sequence shown in the sequence shown in the slide, the session consistency is not guaranteed. The problem is that the read of account B may be done before commit prepared of global transaction 1. The solution is to wait for commit prepared to read the updated results. After commit prepared, the result of the transaction is determined, and users can read the updated value. Of course, this idea does not work as is, since the global transaction 1 is invisible in the snapshot in shard B. So we need to customize the snapshot architecture. Once again, we look back at the structure of the snapshot. This slide illustrates the snapshot in shard B. In this case, transaction 103 is a global transaction 1 and is prepared. It is invisible in the current PostgreSQL. The solution here is to change its visibility. In this case study, we regard prepared transactions as completed at the time they are prepared, even if they are not finished. In this slide, transaction 103 is now shown as blue box, meaning visible. Of course, its final state of committed or aborted is not fixed, so we wait for such prepared transactions when accessing tuples modified by them and determine the tuples visibility. In this slide, when scanning the table, if we find prepared transactions in the snapshot, we wait for them to finish. Here, we find transaction ID 103 as the prepared transaction, so we wait for it to finish. Depending on whether this transaction is committed or aborted, one of the tuples in the table will be visible and returned as a result. Now, I will explain how this method is implemented. Let's first review the flow of executing a point query. In this case study, we need to customize the snapshot architecture and tuple visibility determination. To achieve this, the case study modifies the structure of snapshot data and get snapshot data. It also needs to modify heap tuple satisfies visibility and its query. First, I will explain the modification to the snapshot data structure. The method adds a field to snapshot data to hold transactions that were prepared when the snapshot was taken. This slide shows snapshot data in the current PostgreSQL. The XIP field contains in-progress transactions when the snapshot was taken. In this case study, we add the XTPC field. This field records prepared transactions. With this change, the XIP field now means in progress but not prepared. The next modification is for tuple visibility determination. It is done by the heap tuple satisfies visibility function. This function takes a tuple and a snapshot as arguments and returns whether the tuple is visible according to the snapshot. Its source code is shown here. There are several types of processes depending on the type of snapshot, but the important one here is the MVCC, which is handled by the heap tuple satisfies MVCC function. Here is its source code. This function is so large that I cannot explain all of it, so I will limit the discussion today to just a part of it. This if statement indicates when xmin might not be committed. In this case, we need to confirm if it is committed or not. First, this function checks xmin according to the given snapshot. This is done by the xid in MVCC snapshot function. The function returns whether the given transaction is treated as in progress based on the snapshot. The method in this case study waits for the given transaction to finish if it is marked as prepared in the snapshot. After returning, the status of the transaction will be finalized. Then, heap tuple satisfies MVCC reads the commit log and determines whether xmin is committed or aborted. Prepared transactions are already finished, and we can see their final status and read the updated results. Let's return briefly to earlier figure. The problem is that in snapshots before commit prepared, global transactions are marked as in progress and are thus invisible. The method in this case study modified the snapshot architecture to wait for such transactions. So transaction 1 is now visible and we can ensure session consistency. Now I would like to present a simple experiment we conducted with the SmallBank benchmark to test the performance of the method in this case study. The slide shows the schema and queries of the SmallBank benchmark. It has 3 tables for users in the bank and their accounts. The benchmark issues 6 types of queries. For example, it has queries that make balance inquiries. This is the configuration of the experiment. It is a cluster configuration with 1 coordinator and 4 shards. Benchmark clients issue queries to both the coordinator and the shards. If a query involves multiple shards and accordingly needs to be organized into distributed transactions, the clients issue the query to the coordinator with 2PC. In contrast, if a query is enclosed within a single shard, the clients bypass the coordinator and issue it to shards directly. This improves the overall performance in terms of throughput and latency. Here are results. The left chart shows throughput and the right chart shows 95th percentile latency. The blue line denotes vanilla PostgreSQL and the red line denotes the method in this case study. This slide shows the case where 1% of all transactions involve multiple shards and are distributed transactions. As we can see, our method performs comparably to vanilla PostgreSQL, achieving almost the same high throughput and low latency while ensuring session consistency. This is the result when the distributed transaction rate was 10%. Our method achieved just as good a result as in the 1% case. I will show 50% case. Even when half of transactions are distributed transactions, there are no performance penalty with the method in this case study. These results demonstrate that the method is very effective. This method features a modified snapshot architecture, so you may be wondering how is its correctness. In general, this method is not suitable for snapshot isolation because transactions that were in progress when the snapshot was taken are visible. Its behavior is different from the snapshot isolation in PostgreSQL. However, it takes advantage of the user-specific assumptions described in the slide. The assumption is that read committed is enough as an isolation level, as it allows reading the latest data for each command. In PostgreSQL, if 2 transactions write the same tuple, the successor waits for the predecessor and reads the updated tuple. This is called read committed updated checking. The method in this case study is similar to this. Of course, there is high potential of infinite wait, so users should utilize it carefully. If users understand these restrictions and assumptions, they can achieve significant benefits that are not available with conventional transaction methods. This highlights the strong need for introducing custom transaction methods. I will now summarize this case study. The method has a very simple implementation. It ensures session consistency even when users bypass the coordinator and access shards directly, and it can resolve conflicts at a very fine granularity at the tuple level. Experimental results with the SmallBank benchmark show a very high performance. These findings demonstrate significant advantages that are not available with conventional transaction methods. However, as I said just before, the method differs from standard snapshot isolation, and there is the potential risk of infinite wait. So it is preferable for this method to be implemented as an extension for users who can understand it deeply and use it carefully. Moreover, XTM is needed if users wish to avoid modifications to PostgreSQL core. XTM is effective for this case study. This slide shows the APIs that XTM can replace. In this interface, both getSnapshot and isInSnapshot are effective replacements. Lastly, I will discuss XTM. The first point is that user-specific requirements are constantly diversifying. The situation surrounding PostgreSQL has changed greatly since 2015. In 2015, when XTM was first proposed, sharded clusters were underdeveloped in PostgreSQL, and distributed configurations were limited to a few users. However, today, PostgreSQL is widely utilized and features many distributed configurations, such as built-in sharding or other extensions. And cloud providers also offer a wide range of managed distributed databases. Many users are taking full advantage of these technologies. So, no single transaction manager can meet all these increasingly diverse requirements. XTM is thus significantly rising in importance. While XTM is effective, there are few things we need to keep in mind for its implementation. Here, I should ask one question. Does XTM provide enough APIs for transactional extensibility? If XTM is merged into the PostgreSQL core, we need to maintain it forever. To provide APIs for XTM, we must confirm that the APIs can satisfy a wide range of needs for transactional extensibility and are sufficient. Finishing the design of XTM too early has potential problems from this point of view. We need to implement various distributed transaction methods, including lightweight or user-specific ones, through XTM, and discuss what extensibilities are missing in the current proposal to improve XTM designs. A variety of user-specific examples is needed for discussion in community. I hope today's talk will be the beginning of such a discussion. Then, what exactly is missing in XTM? Other extensibility may be required to implement various kinds of transaction methods. Modifications to Transaction Manager affect a wide range of components in the PostgreSQL system, such as replication, crash recovery, and word logging. Indeed, the case study presented in this talk may have some problems in web application. Rather than simply making the transaction manager pluggable, we need to explore which modules of PostgreSQL will be affected by the custom transaction methods and should be pluggable. Finally, I'd like to conclude today's talk. As distributed configurations continue to spread, the requirements for transactional methods are now diversifying, and existing methods fail to meet them. The current PostgreSQL lacks transactional extensibility, thus preventing users from implementing user-specific transaction methods as extensions. XTM has emerged as a promising solution, and this talk has presented a case study that highlights the potential of XTM to meet diverse user-specific needs. The case study addresses the banking system and shows that XTM is effective to implement a user-specific transaction method while maintaining high performance. To merge XTM into the PostgreSQL core, we need to discuss other extensibilities that are required to implement various kinds of transaction methods. XTM is growing in importance, is worthy of continued discussion. These are references. Thank you so much for listening to my presentation.